If you live near the coast, you have seen the ocean creep up the beach, then slowly pull back twice every single day. And if someone asked you why, you would probably say, the moon's gravity pulls the water toward it. That sounds right. But here is the problem. While the ocean rises on the side facing the moon, it also rises on the exact opposite side of the planet, as far from the moon as you can possibly get. If the moon is just pulling water toward it, why would the ocean also bulge away from it? Something weird is going on. Let us start with what most people get right. The moon has gravity and it pulls on everything on Earth, including the oceans. The water on the side of Earth closest to the moon feels a stronger pull, so it gets tugged outward into a bulge. Makes perfect sense. But here is where the standard explanation falls apart. Most people stop there and never explain the second bulge. Some say the water on the far side just gets left behind. Others blame centrifugal force. Both of those explanations are wrong. The real answer comes down to one word: gradient. Tides are not caused by the moon's gravity pulling everything in one direction. They are caused by the difference in the moon's gravitational pull from one side of Earth to the other. Think of it like this. Imagine you are holding a stretchy rubber ball. If you squeezed it equally from all sides, it would stay round. But if you pinched both ends and pulled, it would stretch into an oval. That is exactly what the moon's gravity does to Earth's oceans. The pull is not uniform. It varies. Here is how the gradient works. The ocean water closest to the moon feels a stronger pull than the center of the Earth does, so that water gets pulled ahead, creating the near side bulge. But on the far side, the ocean water feels a weaker pull than the center of the Earth. The center gets pulled toward the moon more than the far side water does, which means the Earth essentially pulls away from that water, leaving it behind in a second bulge. The moon is not pushing water away, it is pulling the Earth out from under it. So now we have two bulges of water, one facing the moon and one on the opposite side. These bulges stay roughly locked in place relative to the moon, but Earth is spinning underneath them, completing one full rotation every 24 hours. As your spot on the planet rotates through a bulge, you experience high tide. As it rotates out, low tide. And since there are two bulges, you pass through both of them each day, giving you 2 high tides and 2 low tides roughly every 24 hours. The ocean is not really rising and falling. You are spinning through a stretched out shell of water. Now here is a question that trips people up. The sun is way more massive than the moon, like 27 million times more massive. So why does the sun not dominate our tides? Because tides depend on the gravitational gradient, not total gravitational strength. The gradient gets weaker with distance, and it weakens fast, following an inverse cube law. The sun is about 400 times farther away than the moon, so even though its overall pull on Earth is much stronger, its pull barely changes from one side of our planet to the other. The moon is close enough that the difference in its pull across Earth is significant. But the sun does still matter. Its tidal effect is about 46% as strong as the moon's. And when the sun and moon line up, either during a new moon or a full moon, their tidal forces combine. The bulges get bigger, the highs get higher, and the lows get lower. These are called spring tides, and they have nothing to do with the season. The name comes from the old word meaning to leap or surge. Spring tides happen roughly every 2 weeks, and if you have ever been to the beach during one, you know the water seems to come in way farther than usual. The opposite happens during a first quarter or third quarter moon, when the sun and moon are at right angles to each other. Now their tidal forces partially cancel out. The sun tries to stretch Earth one way, while the moon stretches it another. The result is smaller bulges, smaller tidal range, and calmer coastlines. These are called neap tides, from an Old English word meaning scanty. So every 2 weeks, the tides swing from their strongest to their weakest and back again, all choreographed by the geometry of the sun, moon, and Earth. Now, the average tidal range across the open ocean is only about 1 meter. That is barely noticeable, but certain coastlines amplify tides dramatically. The undisputed champion is the Bay of Fundy in eastern Canada, where tides regularly reach 16 meters. That is taller than a 4-story building. Twice a day, 100 billion tons of water rushes in and out of this bay, more than the combined flow of every river on the planet. That is not a typo. Every single river. combined. So why is the Bay of Fundy so extreme? Two things. First, it is shaped like a giant funnel, wide at the mouth, narrow at the head. As the incoming tide gets funneled into a tighter and tighter space, the water has nowhere to go but up. But the real secret is resonance. The natural sloshing period of the bay, the time it takes water to slosh from one end to the other and back, is almost exactly 12 hours. That is nearly identical to the time between high tides, so each new tidal pulse arrives just as the previous one bounces back, and they stack on top of each other, building higher and higher like pushing a kid on a swing at exactly the right moment. And tides are doing something else that most people never think about. They are slowing Earth down. The tidal bulges create friction as Earth rotates underneath them, and that friction acts like a brake. Every century, our day gets about 2.3 milliseconds longer. That does not sound like much, but over millions of years it adds up. 600 million years ago, a day on Earth was only about 21 hours long. And all that rotational energy Earth is losing? It is being transferred to the moon, pushing it farther away at a rate of about 3.8 centimeters per year. So the next time you are standing on a beach watching the tide roll in, remember, you are not just watching water move. You are standing on a planet being gently stretched like taffy by an object 384,000 kilometers away. The ocean on the far side of the world is rising at the same time yours is. The sun is adding its own tug to the mix. And with every wave that washes over your feet, Earth spins a tiny bit slower, and the moon drifts a little farther into the dark. Tides are not just water going up and down. They are the universe quietly reshaping our world, twice a day, every single day. If you like this video, check out one of these, and don't forget to subscribe.